Okay, so let us next see subsets of the set of real numbers. Now, the set of real numbers, of course, has many different kinds of subsets, infinitely many subsets, many different types of subsets, but some subsets are more important than others. And the first few we are going to see today are already familiar to us. And they are, of course, these sets. The set of natural numbers, which we denote by n and which is specified in the roster form like this. Then the set of integers, that is the set of integral numbers. Integral means non-fractional. It's denoted by capital Z and the set is specified in the roster form like this. Unlike the set of natural numbers, this set is, if you want to say, it is doubly infinite. When you express it in roster form like this, you have to use the ellipsis twice. Okay, it goes indefinitely on that side and it also goes indefinitely on this side, whereas this goes indefinitely on only one side. It starts somewhere and then keeps on going without any end. And then after these, we have the set of rational numbers. We know that this set cannot be conveniently expressed. In fact, it cannot be expressed in roster form because there is no definite pattern in which you can write the rational numbers. In what sense? Here also actually we haven't written all the natural numbers. That is not possible because there are infinitely many natural numbers. We can only hope to show finitely many of them. But in spite of not being able to write all the natural numbers, we at least know how the list is progressing, in what pattern the numbers are coming, so that you can say what the next number is. 4. You start with 1 and then keep adding 1 every time you write a new natural number. That is the pattern. Similarly, there is a pattern to how the integers are appearing on this list. However, no such pattern exists in which you can conveniently write the rational numbers in a list. However, you actually theoretically can write, but you cannot give a definite pattern. I am not going to go too deep into this. The thing is that we know that the set of rational numbers cannot be expressed using roster notation. So only we have to rely on set builder notation. And in set builder notation, the set of rationals is of course this. It is the set of all x such that x is of the form p over q, where p and q are integers and q is not equal to 0. I have seen a tendency of people not remembering this part. It is very important to keep in mind that p and q need to be integers. People only tend to remember that x is of this form and q is non-zero. That, however, if you just ignore this part, then many numbers, many real numbers which are not rational will become rational. For example, you know that the square root of 2 is not rational. However, if you ignore this part, you can write square root of 2 as square root of 2 over 1. So using your modified definition, this should be rational, but that is clearly not true. So do not forget this part, that p and q, numerator and denominator, should have integers. Okay. And after these three sets, actually there is also the set of irrational numbers, just like this one, root 2, square root of 2, square root of 5, cube root of 2, cube root of 5, or other higher roots. Okay. Now that set, the set of irrational numbers, does not have a standard symbol, although in this text the symbol capital T, for some reason I don't know why, has been used to denote the set of irrational numbers. So it is the set of all x such that x is a real number and x is not a rational number. X does not belong to the set of rational numbers. Examples, of course, in the text, these examples have been given. These are irrational numbers. None of them can be expressed as a ratio of two integers. So they all belong to T, and none of them belongs to Q. In fact, that's what T is. T is precisely the set of those real numbers that are not in Q. Now, the way these sets are related to one another using the subset relation is this. First, the set of natural numbers is a subset of the set of integers, which in turn is a subset of the set of rational numbers, which in turn is a subset of the set of real numbers. Additionally, the set of irrational numbers is also a subset of the set of real numbers, and the set of rational numbers is not a subset of the set of irrational numbers. In fact, no element in Q is in T, because that's the definition of T, and that is why Q is not a subset of T. We just need one element of Q to not be in T in order for Q to not be a subset of T. But in this case, the situation is more drastic. No element of Q actually is a subset of T. There is a better way of expressing this situation using something known as intersection of sets. But we will see that later. Okay. Now, besides these well-known sets, there are other subsets of the set of real numbers, which are called intervals. So next we discuss that. Let me first give the definition itself. Intervals as subsets of R. Definition. There is no point in maintaining those numbers, okay? The concept actually is what matters, not the numbering. Let A and B be two real numbers such that A is less than B. We consider the following 4 subsets of R known as intervals. Okay, 4 different types of subsets are there which are determined by these two numbers A and B, and they are called intervals. So we are now going to see their definitions. And these subsets have special symbols to denote them. Instead of denoting them by, say, capital letters like A, B, or say N, Z, Q, instead of those, we have special symbols to denote them. For example, this is one of such symbols. And this is the set of all real numbers x that lie between A and B in this manner. In other words, we have A, which is a real number, we have B, which is another real number. If you think of them visually, A denotes a point on the real line, B denotes another point on the real line. A lies to the left of B. Okay. In fact, let me just draw this thing. So this is our real line which extends indefinitely on either side. That we understand. Alright. Say you have A here and you have B here. So what we are saying is that the above subset is precisely the set of those real numbers that are greater than A and less than B. Geometrically, this corresponds to the set of those points on the real line that lie to the right of A and to the left of B. In order to draw this set on the real line, we use a technique like this. You see, we have to somehow, draw a diagram in which this should be clear that A and B, these two numbers themselves are not elements of this set. For example, A itself is not greater than A. So A does not belong to this set. Similarly, B itself is not less than B. So B does not belong to this set. So what we do, we draw circles, okay, white circles. White circles means like this. Around that point on the real line which denotes A. It's as if this circle has that point which denotes A on the real line as its center, but of course it has a small radius. Similarly, taking the point which denotes the number B on the real line as center, we draw another circle there. And what we do, we make the line segment whose ends are these 2 points A and B bold. Okay. We make it bold. Okay, a little thicker than the entire line, the actual real line. And this denotes geometrically this set or this interval. For example, if you take, say, A equal to 1 and B equal to 3, then 1, 3 is the set of those real numbers which satisfy these inequalities. Now let us take some real numbers and see whether each one of them belongs to this set or not, belongs to this interval or not. 1 itself does not belong to 1, 3. 3 does not belong to 1, 3. But those numbers which lie in between 1 and 3, all of them will be in 1, 3. For example, 2 belongs to 1, 3. And not just that, rational numbers will also be there. For example, 1.5, which is also of this form 3/2, so that you know it's rational, only it's expressed in the decimal representation like 1.5. This also belongs to 1, 3. But additionally, there are irrational numbers also in this interval. For example, square root of 2 also belongs to 1, 3. How do you know this though? If you rely on the decimal representation of square root of 2, then you can readily say that it is approximately 1.414215, whatever it is, okay. But there is a better way of verifying that square root of 2 belongs to 1, 3. You see, we already know something. We know that we have these inequalities, right? And this square root function, okay, I am using the word function, but let's just take it lightly. A function is something in which you input a value and it gives you back an output. So instead of writing root 2, if I write root x, say, then x is my input and the square root function gives me the square root of x. Okay. Now from properties of square root function, we know that whenever we have positive numbers like this and we have inequalities like this, then we can take square roots of those numbers and the inequality direction stays intact. Which means that from these inequalities, I will get this. And that is just square root of 1 is 1, square root of 2 of course is what it is, and square root of 9 is 3. Well, if you just simply say square root, actually every positive number has 2 square roots. For example, one of the square roots of 9 is 3 and there is another one, minus 3. However, when we use this symbol, we mean the positive among those 2. Okay, so that's why we have this. But then root 2 is a real number satisfying these inequalities, and that is why root 2 belongs to this set. And this type of intervals where these are called the end points of the interval. This is left end point of this interval, which basically is nothing but a set after all. And this is the right end point. This type of intervals where none of the endpoints themselves is an element of the interval is called an open interval. That is, an open interval is an interval in which none of the endpoints is an element of the interval or of the set. Such intervals are called open intervals. There is another way of denoting this. There used to be another symbol for this set. In old usage, that same set is written like this. However, it looks a little weird and it has fallen out of use. Nobody uses it now. Okay, it is obsolete. So this is no longer used. But anyway, this type of intervals are called open intervals. It's as if you have an area, a plot of land, and A and B correspond to the fence around the area. If there is no fence, then the area is open. Okay, so in that sense, it's an open interval. Here, however, we do not have a two-dimensional area. This is a one-dimensional line segment. That's why it's line segment. Next comes another type of interval. Again, a set like that, but this time it will be different from this, in that something different will happen at the endpoints, at the boundary points. Instead of using parentheses or round brackets, now we are using square brackets. It is also the set of all real numbers x, but this time we change the inequalities like this. Instead of having strict inequalities, we have ordinary inequalities. Note now that A and B are both elements of this new set. Why? Because A is not greater than A, but A is greater than or equal to A. Because A is equal to A, similarly B is not less than B, but B is less than or equal to B. Now, how will you draw this interval though? In this case, again you draw the line and say this point denotes the real number A and this point denotes the real number B. But this time the circles are drawn black and making the line segment thicker. That is just like before. Oh, by the way, I forgot to say why we draw the circles at all. See, you know that actually the point which really represents the number A is the center of that circle. So what the circle does, its purpose is to prevent this line from touching that point. And that indicates the fact that the point A itself is not in the interval. But everything that lies to the right of A, it is there. That of course we cannot possibly show by drawing a circle like that, because if you think about it, there are some points on the line which the circle takes inside of it. So ideally they should also lie outside the interval, at least in this pictorial representation. But you can understand, of course, we cannot draw a circle of infinitely small radius. It just indicates the fact that this line segment does not touch either this point or that point. That is the purpose of the circle. Here, however, in order to show that no, those points are also included, we draw black circle. Okay. So if we take these same numbers, A equal to 1 and B equal to 3, this time this interval is this set, this subset of the set of real numbers. The difference though is that neither 1 nor 3 belonged to the open interval 1, 3, but both 1 and 3 belong to the closed interval. We call this type of intervals closed intervals. And there is in fact no point writing the other things because they are also in this closed interval. Such intervals are called closed intervals. So a closed interval has both of its boundary points inside of it as elements. It's like you have that plot of land and the fence is included, okay, entirely. So now it is closed. In that sense, these are called closed intervals. Now the observant reader will immediately notice one thing, namely, the open interval a comma b is a subset of the closed interval a comma b. Why though? You just look at these two examples. Any point, any real number x that satisfies these inequalities automatically satisfy these inequalities also, and so will be inside this. That's it. That's why this is a subset of this. However, actually this is a proper subset of this. Why? Because there are 2 points in this set, 2 elements in this set which are not here. Those 2 boundary points. Okay. So to express that, if we recall what we said about proper subsets, although this symbol is not available in the text, but still I am using it because this is my own remark, okay, about the relationship between these 2 intervals. But there are 2 other types of intervals. You can imagine what we are going to see next. One of the boundary points is an element of the set, but the other one is not. And depending on which one you choose to keep in the set and which one you choose to throw out, you get 2 more. And they are these. And accordingly the symbol also changes. That means, see, because we have decided to use brackets or square brackets to denote those intervals which have the boundary points in them, and round brackets to denote those intervals which do not have the boundary points in them. So we can combine the use of those 2 types of brackets. Okay. For example, here this will be such an interval which has A as an element in it but not B. And accordingly in its definition, the inequalities will change. So x can be A, but x needs to be strictly less than B. And there is another one which does not have A but has B. In the old notation, these intervals will be denoted in this very strange manner like this. For example, this one and this one will be denoted like this. It looks very ugly. Okay. So this time the inequality towards A on the side of A will be the strict inequality, but on the side of B it will be ordinary inequality, where there is an option for equality. Now, without going too much into these two things, I am just going to mention this. A belongs to this, or in fact, you see, although these are simple notions, but still, when you are trying to understand something, never use variables. Always take some specific values and then see what happens. We continue to take A equal to 1 and B equal to 3. So we get this interval and we also get this interval. Now the thing we should note about these intervals is that 1 belongs to the first type of interval and 3 does not belong to that interval. Similarly, 1 does not belong to the second type of interval, but 3 belongs to the second type. Okay, and these two types of intervals, they are collectively called half open intervals. If you want to be more specific, sometimes this type of intervals are called closed open interval, and this type of intervals are called open closed intervals. Besides these four, actually there are other subsets also like intervals, and they are also called intervals, which are not talked about in this book very systematically, but let me just show them as well. You see, okay, I need to draw these two types also, no? But you now know how to draw them. For example, the first type of intervals will look like this on the real line. A, but because B is not there in the interval, this circle will be white circle, and we make the line segment thicker than the real line. Okay, so this is this interval. And let's also draw the other one. In the other one, A will not be there, but B will be there. So this is the interval open A, closed B. And now we come to the discussion of some other types of intervals which look like these four. However, note that all these intervals, all the four types we have seen just now, each one of them corresponds to a line segment on the real line when we draw them, when we represent them as pictures, as figures like this, geometrically. And the four other types of intervals that now I am going to talk about, they correspond instead to half lines or rays. One of them is this. We started our discussion with open, right? So let me just talk about this first. this is the set of all real numbers such that x is greater than a. This interval has only one boundary. The other boundary is not there actually. So it looks like this. Geometrically it looks like this. This time we use an arrowhead also to indicate that the set goes on and on that side. And we bolden this entire arrow like this. Okay, so it is geometrically, this is the set of all points that lie to the right of A. Arithmetically, it is the set of all numbers that are greater than A. And that's it. Do you see why this type of things are called rays? Because they start at one point and then go in one direction without any end. They look like this, as if it's a light ray, as if this is a flashlight which you have switched on and there is a ray of light emanating from it and going in a particular direction. Okay, so this is the ray. It's called an open ray. Similarly, you have a closed ray. Here, the inequality will be changed from the strict one to the ordinary one. And the figure accordingly is not much different from that one. The only difference is that now that sole boundary point A is an element of the ray. So it is blackened. And there are two others because you can have the ray on that side also. But I need ink first. Now after showing these two other rays, I will talk a little bit about these symbols, plus infinity and minus infinity. So the other two will be, of course, this. One of them is this. If you want, you can write A here, okay, or if you want, you can write B. It does not really matter. This time, it is the set of all real numbers that are less than B. Now there is a right endpoint. These rays had left endpoints because they started at a point and moved to the right of that point. This ray has a right endpoint. It starts at a point and moves to the left of that point. So geometrically, it looks like this. Accordingly, the arrowhead also points in the other direction. Like this. This is also an open ray. Oh, by the way, this is a closed ray. This is also another type of open ray, and this is another type of closed ray. Let me just also, in order to reinforce all these ideas, let me also write these things. P does not belong to the open ray minus infinity comma B, but B belongs to the closed ray minus infinity comma B. And in this case, of course, geometrically we have this. We draw a black circle around the point which represents the number B on the real line. Okay, and B belongs to the closed ray this. Now at first it may seem like not really good names for these sets. I mean, we are calling this ray, for example, a closed ray, but this side is open. See, that is because infinity and minus infinity are not real numbers. They are not numbers, in fact. They are just symbols to represent the fact that something does not end. However, there are number systems in which these symbols are incorporated. However, such number systems are not really as nice as the real number system. They have their own some advantages, but most of the things about them are disadvantageous. Okay, so that's why they are not talked about that much. But in any case, those things are well beyond the scope of this text. We do not have any need to talk about them. Okay, so the fact that these are not real numbers is why we never write infinity and then we write a square bracket. No, never. Just like that, on this side of minus infinity, we never write square bracket. We do write in those other number systems, but that's not needed for us right now. Okay, so these are intervals, and this is another type of closed ray. Now, after having these subsets of the real line, we have the notion of power sets. Let us see that. We have already seen in the video that day before yesterday, we saw that some sets have elements which themselves are sets. You remember that set? This one. I think you remember this set, which in fact I also used to refute one of the sentences written in the text, which is just blatantly wrong. Now, one of the elements in this set is not a set too, but this element is a set. Now, what if we collect subsets of a set and make a set out of them? That is the notion of power sets. Let me straight away give the definition and then we can discuss. The set of all subsets of A given set A is called the power set of A. In the text, you will see that a slightly different definition has been used. The text says the collection of all subsets of A is called the power set of A. Keep in mind that we are going to use the words collection, set, collection and set synonymously. That is, we mean the same thing by both the words. That means a set. However, actually the two words have slightly different meanings in set theory, which also again is something we need not worry about. Okay, for us, whatever we mean by set, collection also means that same thing. So the text says collection, here I am saying set. It means the same thing. Now what is the definition saying? The definition is saying that if you have a set A and you collect all its subsets and then combine them, bring them together and form a set, that set is called the power set of A. Let us take an example. Suppose A is the set consisting of these two elements 1 and 2. The subsets of A are, okay. Now, what are the subsets of A? Of course, first of all, you should not never forget that the empty set is a subset of every set. So whenever it comes to listing all the subsets, you first mention the empty set so that you do not forget. Actually, there is no need to mention the empty set first, but we do so. Okay, customarily that's the way of writing things. But then these singleton subsets of A exist, and there is this subset also, which is A itself. You remember, while discussing about the subset relation, we mentioned two things, that the empty set is a subset of A and A is also a subset of A. That is why both the empty set as well as the set itself appear on this list. Now we collect all these things and make a set whose elements are these sets. That is the power set of A. So, the power set of A is, because we have all the elements, we can use the roster method. You write the list separating the elements by commas and then enclose them within square brackets. When we see this type of sets for the first time, we may get really confused about these brackets and the commas. Be very careful about them, okay? Do not mix them up. You view this entire thing like this. You forget about the outer curly brackets. You think of the entire thing as a list. In this list, there are the elements of this list are themselves sets, which themselves may have more than one element. For example, this one. So, as a set, it will have its own commas. But outside, of course, we have commas. So, you interpret these things properly, and so that we do not get confused about this entire thing. So the outer brackets are sometimes drawn a little bigger than the inner brackets. the power set of A is denoted as P of A, power set of A. So for this particular A, P of A is equal to this. In order to make the representation a little easier to understand, instead of writing that, I write A. Same thing, I can write A itself there. Note that the number of elements in this power set is what? 4. 1, 2, 3, 4. And 4 turns out to be 2 square, where this exponent 2 is the number of elements of A. Let us do a little experiment. Instead of taking this 2 element set, let's take a 3 element set. Suppose we take another set B, say, which has these 3 elements. Of course, you need not always take natural numbers. Let us instead take English letters A, B and C. Now we are going to straight away write the power set. Okay, power set of B. The empty set you write first. There is no need to write it first, but we do so. Okay, and then we go for the non-empty subsets. You have the singleton subsets, so you write them first. In other words, while finding the subsets of a given set, we increase the element number, and that way we find all the subsets. What are the 2 element subsets of this set? AB, BC and CA. What are the 3 element subsets? There is only one 3 element subset of B, which is B itself. Now let us note the number of elements in P of B. 1, 2, 3, 4, 5, 6, 7, 8, which turns out to be 2q, where that exponent again here also is the number of elements of B. So there seems to be a pattern in which you can write the number of elements in the power set in terms of the number of elements in the original set. So we have seen a 2 element set, a 3 element set. Why not 0 and 1? Okay, now here you have to actually be a little careful. What are the subsets of the empty set? The empty set, of course, is a subset of itself, which is a 0 element subset. Can there be a 1 element subset? No, because the empty set is empty, so there is no 1 element or 2 element or 3 element subsets. This is the only subset of the empty set. As such, the power set is a singleton set. So this is 1. However, very nicely here also, this is 2 to the power 0, where 0 is the number of elements in the empty set. So in this case also, this pattern prevails. It's still working. Let us take another set C, which has only 1 element. Say, just to make things a little strange, that only element is 10. What is the power set of C? It of course has the empty set, and then a one element subset of C, which is C itself. So this is the power set of C. How many elements are there? 2. The number of elements in P of C is 2, and here also 2 is 2 to the power 1, and that exponent is the size of the original set, because the original set was a singleton set. In general, if A is a set with n of A equal to n, say some non-negative integer, the number of elements in A is n, then the power set of A has 2 to the power n elements. And in fact, this formula itself is the reason why we call this set a power set. Okay, the power set. Power sets of infinite sets also exist, if one tries to think about that. One can consider this also. However, the number of elements also will be infinite. But that's not because infinity is equal to 2 to the power infinity. Always be careful to not write things like this. Okay. No matter how plausible these things look, you feel like this should be true. Multiplying 2 infinitely many times should be infinity. But multiplying 2 infinitely many times itself has no meaning. Okay. In general, what at this stage we can say about this P of n is that it's very big and it's infinite. There are other things that can be said about this, but I am not going to go into those discussions. And lastly, we have the notion of universal set. In A, let me first write what is written in the text. In A, particular context, all the elements may be maybe elements of a large set, and all the sets are subsets of that large set. Then that large set is called a universal set. Now, simply reading this, it may sound a little confusing. So, what this paragraph is saying is that, say you are having some kind of discussion about some particular thing. Say you are discussing about number theory. Okay. It's an area of mathematics which at the most elementary level talks about integers and their divisibility, prime numbers. These are some things which come at first in a number theory discussion. So in the context of number theory, at least at a primary level, all you will be talking about is integers, okay, the set of integers. So whatever you talk about are going to be about integers or about some special sets of integers. For example, the subset of this of all even integers. Maybe for some reason you are discussing about even integers. This is a subset of Z, or the subset of Z of all the prime numbers. This second subset is in fact a hot topic of discussion among number theorists, and there are so many things still unknown about this subset. Okay, so all these subsets of interest are subsets of this single set, and all the elements of interest in a number theory discussion at this level are integers. So in that sense, you actually do not have to go outside of the universe of integers, and that's why in that particular discussion, this can be taken as a universal set. Instead, if you have a discussion about real analysis, which is an extension, which is another area of mathematics, it's an extension of the subject calculus. Okay. Then at an elementary level, all you will be talking about are real numbers, sets of real numbers, subsets of real numbers. For example, we have already seen some subsets today. Okay. So in that discussion, where the real numbers are the main objects of interest, sets of real numbers are objects of interest. So all of them are either elements of R or subsets of R. So in that discussion, this is a universal set. So in a given context, all the elements may be elements of a large set, and all the sets may be subsets of a large set. So in that context, that large set will be called a universal set. We denote a universal set usually by the letter capital U. And we will see later that when we draw Venn diagrams of sets, usually ordinary sets in a Venn diagram are drawn as circles or ellipses, or maybe some more irregular area like this closed area. However, a universal set usually is drawn like a rectangle or a square. Okay, it's customary to do so. So this section ends here itself. After this, of course, we have the end section exercises, which we will solve next. But anyway, that's just it for tonight. So see you in the next upload. Until then, this is me, Lucifer, from A Mathematical. Have a nice day.